Hi, everybody. This is Joanne Manister, Science Goddess on Twitter, here with my co-host Jeff Schomeyer for Read Science. And our guest today is Natalie Starkey, who we had on our show in November 2018. Thanks for returning. Back then, we talked about her book, Catching Stardust, about comets, asteroids, and the birth of the solar system. And I remember very vividly at the end asking, are you going to write another book? And you said, yes, I'm going to write about volcanoes of the solar system.
Yeah.
Almost every other author is coy and they don't quite say, what's happening. And but Natalie was right up front. So I was anticipating your new book for quite some time. This one came out October 2021, Fire and Ice, the Volcanoes of the Solar System. And I love this book because it's sort of like geology in a nutshell. It's about volcanoes, but the solar system. And so it's very cool. Welcome, Natalie. Thank you for joining us.
Thanks for having me back. It's great to be here.
There is huge amounts to talk about just because, like Joanne said, you do geology and the volcanoes, and you cast a very wide net for talking about the science. And I found that very useful and very interesting. So that's just one positive thing to say. Now I'm going to try. To share a picture.
Okay. Do I need to do something here? Yep, I have to add it to the stream.
Okay. Oh, there we go.
Good. I'm going to move it over here a little bit. That looks terrific. Now, do you recognize this picture, Natalie?
Well, yeah, I think I can probably guess.
I think you can. I'm going to I saw that and I started reading about Voyager and Io, and not everything about getting older is a fun thing. But one fun thing is that I remember when this picture first appeared in the popular press.
Oh, wow.
And that was, I have the date, that was around April of 1997 as Voyager.
97 or 1979?
1979. Thank you.
Yeah, I was in high school, so
yeah,
everyone's calculating my age now.
That's right. Voyager 1 doing its flyby of Jupiter, and it took this picture, which caused, I seem to remember it on the cover of Scientific American. It was an absolute sensation at the time. And the question that sort of like I hope gets us into talking about everything in the book is, why was this picture such a sensation at the time?
Yeah, so this picture is of Io, as you said, which is a moon of Jupiter. Now, really before Voyager went out there and started exploring the outer solar system, and this was really, the Voyager was made up of two missions, Voyager 1 and 2. We hadn't been out to the outer solar system before, so we really didn't know what to expect. But what we did think was that everything was going to be cold and dead because everything was so far from the sun. And these small moons that orbited around the large planets were probably just icy and cold and not doing anything. And, this was the really exciting thing about Voyager. It just completely unearthed these worlds that were active and so unlike we expected. And, Io, out of all of them, is probably the most surprising because it's not even made of ice. Its surface is rocky, just like the inner planets, just like Mercury, Venus, Earth, and Mars, and like our own moon. And the next really exciting thing is that it's active today. It's got volcanoes erupting on its surface. I think Voyager spotted at least 5 eruptions happening, during those quick flybys. And then since then, with every mission that we've gone past Io with, we've seen eruptions happening. So what you're seeing in this image is the curve of the surface of Io, and this is a plume of volcanic material shooting off the surface into space. And some of these plumes shoot kind of 200 kilometers high off the surface. And they're made up of different things. They've all been studied. There's lots of different types of plume that we look at, but they can be very dusty. They can be made of lava. It's all different things, or very sulfur rich. But what this shows us is that Io, this tiny moon around Jupiter, is a really active world, which was completely unexpected, and really opened up, science in the outer solar system. Really opened up what we knew to be true, and opened up loads of new science possibilities to investigate.
As we've talked to people in the past couple of years, particularly, one thing that has been on my mind, and which you mention more or less directly in the book, is the arrogance of the Earth-century viewpoint when it comes to the lack of imagination we have for what might be going on in the deep oceans, in the clouds, in the wherever that we've never been to yet, and particularly here in other bodies in the solar system. And so we just said, oh, they're too far from the sun, they're all dead, they're icy, they're just sitting there. And here's the first ever picture of something that we can talk about, whether it's a volcano or what it is, but of something active happening on a planet that was other than Earth. And that's that was revolutionary. It was such an idea that something could be going on. It was very exciting.
Yeah, and I think you're completely right. And I mentioned this in the book quite a bit, that, it is this Earth-centric view that we have our own planet, which is beautifully active, and we host life, and we can support life because of our active systems. And that's because we're active geologically inside our planet. It's warm, and it's creating processes within and on the surface. And then we look to our moon, which is, this moon, which is quite like lots of other moons in the solar system in terms of its size, but it's completely dead. It's a cold, dry moon, and it's not active today. So the expectation was that when we looked at moons elsewhere in the solar system, and actually back then we didn't even know about all the moons that were out there. We didn't know there were 79 moons around Jupiter, for example. But we expected them to be just like our own moon, because we just thought, well, these small bodies will have probably cooled down. They had a lot of heat to begin with, and that was because of the heat from the collisions that created them, and all that kinetic energy is turned into heat that creates those worlds. And they've cooled down. They've had 4.5 billion years to cool. They've lost their heat into space because they're small, and they're not going to be doing anything now. But actually, we went out, and the Voyager missions were, really breaking the way with that, and we found that actually there were a lot of worlds out there that didn't have cratered surfaces like our own moon, and the craters on our moon show us that the surface of the moon has been bombarded with comets and asteroids over the years, and it's not been able to do anything about that. So it's not been able to resurface its outer surface over that time. So when we look at our moon, we know that it's been dead for a long time. But when we go to these other moons in the solar system, they've got, smooth surfaces, or they've got surfaces that show interesting geological features like mountains and glaciers and different things like that. So we know that they've been impacted by comets and asteroids over the years, over 4 billion years of history. But if we can't see the effects of those impacts, we can't see those scars of the craters, then we know that they've been able to resurface themselves. And this tells us so much about the inside of those worlds, that the inside of those worlds must be warm to create surface processes. And this was really the moment when we got out there. And it wasn't just Io, as I'm sure you probably got some questions about lots of the other moons out there, but we soon saw that actually our own moon is a bit weird, in fact. All the other moons are kind of the normal ones, and we need to kind of recenter our thinking out there into the outer solar system about what we're seeing out there.
One other theme that I don't know whether it was explicit in your mind, but which comes out and I think is really important for non-scientific readers. And this feeds into that, because it's, to some people, this is just a picture. So what? It's a photograph. Is this really science? And I've heard people complain, it's like, oh, they're going to spend $10 million to go and take some pictures of some planet. But to those of us who work in science, we know that you start with small things, you start with insignificant things, and I think even as you called it, things that almost no one else believes is something that can matter, that nevertheless is a piece that fits into this very large web that we're always building called science, that is filled with inferences and also conclusions and implications for everything that goes on. So you can infer from a little bit that's going on. It has to fit into a much bigger picture that is all of science, which is pretty unforgiving sometimes. But already you're describing this, and it's like, this was just a picture. But look at all that you're able to deduce just from the fact that, oh my God, there's a moon that has something going on, and you're telling us things about how fast it's cooled over its history, what its interior must be like, what these materials might be made of from what we know about, oh, maybe how cold it is, new ideas about sources of internal heat. So as we go, I'm going to have that in mind too, of all these little pieces and how they fit to make this magnificent edifice that now is a vastly greater understanding of everything that's going on in the solar system compared to when I was in high school and I first saw this picture, when, yep, it was just a bunch of dead cold moons, and why would you even bother? Although Saturn's rings are pretty.
They are, but no, you're completely right. And I think with space missions, the first thing we tend to do is try to get images. Like most, when we go out for the first time to look at a new moon or a new planet or somewhere new in the solar system, the most important data that we get are images, because we, as geologists in general, the people that are looking at these images tend to be geologists by training. We can look at landforms and surfaces and understand a lot about how they were formed and what that can tell us about that body. So before we even make chemical measurements or anything else, if we just see an image of somewhere and see what's going on that surface, I mean, you take Pluto, for example, that was the classic example. We got so many images of Pluto, and look at the data we've been able to get from that, understanding how those different parts of Pluto had formed and that it's probably still active today. All of this stuff builds into the fact that we just get a bunch of images, and you wouldn't think it would be that important. But, as I was always told at school, an image is worth 1,000 words. And I think, well, it's probably worth more than that, because when we're going out into space, we need to see what we're looking at, first of all. So, I've recently been learning a lot about how we image in space, the cameras that we send out, which isn't something I really touched on in the book at all, but it's really super interesting, because we need to design spacecraft that can withstand the extremes of these conditions in space, the extreme radiation. Cameras and electronic equipment doesn't like extreme radiation environments. So that's a really interesting part of space exploration, how we design those instruments to withstand those conditions and then get the images and the data that we need. So yeah.
So to the scientific eye, photographs can be quantitative, and you can make measurements. And a fun example is that it's like, what do you call it? Where you count the density of craters on a surface.
Yeah, it's literally crater counting. Yeah.
Crater counting. And a lot of unexpected conclusions, unexpected to the layperson, can follow from that tell you a lot about the history of the planet.
Yeah, it sounds so imprecise, doesn't it? That you could take just, a picture of a region of the moon, for example, where we've basically based it on, and you count the craters in a certain area, and then you can estimate how old that region is. Now, the way we've been able to kind of calibrate it is that we've been to the moon, and we've taken samples of those regions, and we've dated those rocks in a laboratory and done that very accurately, and we can say it's 4.2 billion years old, and we can use that to kind of calibrate what we're seeing in those images. But then, because all of space experienced the same sort of number of impacts over the years, we can then put that to Mercury, or we can put that to a comet somewhere. So that the same kind of thing applies. And very broadly, the more craters you see in a region, the older that region is, and the fewer craters that you see, the younger that region is. So when we're looking at places like Io, it really doesn't have many craters across its surface. All the circular features you see are volcanoes. It's absolutely covered in volcanoes. So we know that it has been impacted by things in the past, and it should have craters all over its surface, but those volcanoes have had lava flowing out of them and have covered over that surface so that we can't see those craters anymore, just like we've seen on Earth, and we have erosion and things that remove that evidence of that past history. Whereas on the moon, we haven't had an active moon for over 3 billion years. So we see that whole history, because it hasn't been able to do anything about those pock marks that were created.
Right. Lots of craters. If I can say, I think it's funny how you talk about cameras. And Carl Sagan is the one famously known for saying, you should put cameras on these things. And can you imagine if we didn't put a camera on Voyager 1,
Mhm.
right? And, he's the one who said, turn it around, take the picture of the Earth,
Yeah.
and even some of the missions for Mars. Yeah, get a camera on there, because what if there's something really interesting and we don't get a picture of it? So,
Yeah.
Oddly innovative and controversial at the time too.
yeah, oh no, what? Put a camera on these spaceships? What, how are we going to get that? So it's very
And I
prescient
think,
for him to do it.
even when those images haven't been useful scientifically, like maybe the one where you look back at Earth and it's the pale blue dot image,
Mhm.
sorry, and it's just a beautiful image, isn't it? And I think I also love one actually from my first book when I talked about the Rosetta mission to the Comet 67P.
Yeah.
And there's this beautiful image where the orbiter has taken a photo of looking back at the comet over its solar panels, and you've got this 4.5 billion year old object in space next to this modern human-made object with these solar panels right next to it, and you're just like, it's just amazing that we're able to, the juxtaposition of those two things in space is just amazing. So it wasn't particularly useful scientifically, but to see that image is just amazing. I absolutely love it.
So what other pieces of equipment have told us more about the crust and the interior of planets? So we can take pictures. What else
Yeah, so
can we
there's
do?
a whole suite of instruments, and it really depends if you're able to land on a body, like we've done obviously with Mars quite a lot. Well, obviously we've sent a lot of orbiters to Mars, and they can measure things in the atmosphere. They can measure things about if there's a magnetic field around a planet, which tells us a lot about what's going on inside the planet. Like Earth, we have a magnetic field because the center of our planet is warm and rotating, and there's metal within it. So whether we can detect a magnetic field on the outside of a planet tells us a lot about what's going on inside. So there's a lot you can do from orbit, and you can also sort of with cameras, you can also do spectroscopy. So you can look down at the surface and find out about the chemical signatures that the rocks are made up of. So that's really informative way. So without even landing on a planet, you can basically map the whole surface. We've done this in great detail with Mercury, for example. There's beautiful maps of the surface of Mercury. Some of the planets are trickier, like Venus, because it's got a carbon dioxide atmosphere, which is very hard to see through. So you need radar to see its surface. So we have radars that look through the atmosphere and see that surface. And then what we do with that is compare that to radars in space looking back at our own planet. So we're trying to understand what those features look like. Is something darker higher up or lower down? Kind of, we have to have some way of calibrating that information and finding out what we think is on the surface of Venus. But obviously when we land on a planet, that's when things get really exciting, or a moon or a comet or an asteroid, because we can start to actually take samples and we can send laboratories down that are very similar to the laboratories we have on Earth that do our chemical analysis. So we take a little bit of a rock sample, we grind it up, we might heat it, we might melt it in some way, and then we can basically extract the chemical information and find out, what that rock is made from. And we can do the same thing back on Earth with, standardized samples of rocks that we might have on Earth, or meteorites that we've got from that planet, for example. With Mars, we can do that. And we can learn much more about what's going on there. So there's so much we can do, but it's really about what questions do you want to answer. You can send any instrument into space. It's not necessarily going to work because, we need to send quite simple instruments into space because it's a horrible operating environment. The labs that I've worked in, I think, goodness me, a truck goes by and it ruins the experiment because you've got to have such a stable environment, and then we're going to send these things on the side of a rocket and expect them to work in these crazy conditions. So we tend to send quite simple laboratories up, but they can still answer amazing questions without bringing rock samples back. And then the final step is, like we're now trying to do with Mars, collect samples on the surface and bring those back to Earth. Because if we've got those samples, we don't need to worry about sending laboratory instruments into space and getting them to work remotely, millions of miles away. We can get those samples back on Earth in our laboratories and, analyze them in so much better detail with all the different instruments that we have here. So there's sort of different levels, but when you're first going out, when you've really never been somewhere before, it's always imaging that happens first, and then some kind of spectroscopy from space, from orbit or from flybys, and then you sort of like delve in through the atmosphere and get down to the surface, and then eventually start drilling into that body like we're doing with Mars.
So you mentioned in the book a little bit before the huge explosion that made it go away, but the Tonga Pai, I'm going to say it wrong.
Yeah,
you said this was the first birth of an island we saw with satellite imagery here on our own Earth. So it shows how important that is. And then I thought it was funny because when I read that, so I read this book in October, and I read it again just last week, just to make sure I remembered everything. And I thought, oh, I just sort of went, oh yeah, that the first time. But then this time it really caught my eye because, of course, we had satellite imaging of it just blowing its top completely off, right?
Yeah, and those images were incredible, weren't they? And I think that kind of thing is fascinating for me, because although we didn't have much ground information in that particular region of Tonga, because it's, you know, very disparate islands all spread out. There's not a huge amount of population in that region, and actually most of the communications in that area were completely decimated by the eruption itself. So it was really hard to get any ground information coming out of the region. So actually the only information we had about what was going on was from the satellite data. So it was like seeing an eruption on another planet. Like, we had no other information on the ground. We could only see it from space. And, you know, we talk about this kind of thing called comparative planetology, where we need to study our own planet in the same way that we study other planets and moons out there, so that we have that comparison. Because it's all well and good, you know, being in a boat and going to that island and seeing what it looks like, but we can't do that on Mars or Io or something. We need to compare it in a way that we analyze it in the same way. So yeah, that eruption, I mean, absolutely devastating for Tonga. I mean, it was such a massive eruption. And I'd obviously spoken about it in previous times when that island was building up, and we were able to study how the volcano interacts with that seawater surface, which doesn't sound important because we don't think there's seawater, you know, at the moment elsewhere in the solar system, particularly at the surface of a planet. But, you know, this is Mars's past. We think that in the past it had surface bodies of water, and it had volcanoes interacting with that surface water. So we need to understand what happens when you get what we call phreatomagmatic explosions. These are when really hot magma, like we had in Tonga, reach very cold ocean water. And what happens, unsurprisingly, is that there's a massive explosion. And that's why that volcano, you know, was so big with that eruption. So we can learn a lot about these other worlds by looking at what's happening on our own planet.
It's happening here.
Which is another theme. I keep seeing these big themes, but and a really important one that's like, we're trying to understand exovolcanoes, and we have to understand terrestrial volcanoes better. And you know, that one. And then I was thinking while you were talking, it's like, well, with the planets that we do orbital missions around, say, before even landing, is all the measurements there are all akin to remote sensing, which has become a very sophisticated thing with Earth orbital satellites. And now we take measurements here that we didn't have ways to measure before. So we see Earth in a new way from developing these things. There's this back and forth between the missions to other planets, the missions to Earth, as NASA calls it, and also then the things that we learn about Earth that we can compare and use as ground truthing for what we see in other places or what startles us. So I enjoyed seeing that whole back and forth, building the chain of inferences again, process going on between what we know on our planet.
And I think the other thing I touched on is the undersea volcanoes, because obviously the Tonga volcano is an undersea volcano, but we have this massive chain of volcanoes under our oceans at the Mid-Atlantic Ridge. For example, we have a lot of ridges under the ocean where we've got two plates spreading apart from each other. Now, these chains of volcanoes, I think the Mid-Atlantic Ridge and around this region is like 70,000 kilometers of volcanoes along the base of the ocean. And most of these volcanoes are extremely deep. They're 2 to 4 kilometers in depth below the ocean. And I think it's kind of hard to imagine, isn't it? Those kind of depths. But it means, on the whole, that we just can't study these features. We've been down to these depths a couple times to try and, with submersibles, to look at what's going on down there and look at the organisms that we find down there and everything that's happening in that kind of ecosystem, that environment that is very different to what we find on the surface of our planet. And it's as hard, if not harder, than going into space in some ways. Because in space, we go on a rocket, we can fly, we sort of understand how to do that. But actually getting down to the base of our oceans, I guess scientifically people don't see it as exciting for some reason, because it's just, it's just part of Earth, it's just the bottom of an ocean, but they don't really know what's down there. And actually, a lot of what we've learned on the few times we've been down to these depths and learned about these environments is actually these environments could tell us a lot about what's going on at some other places in space. And actually, we wouldn't necessarily need to go and drill into other planets and see what's going on there if we could study our own planet in more detail. And I know, there's a lot of subsurface volcano people that will, be loving me saying this, but I honestly think we need to get down there and study these volcanoes in more detail and understand what is going on at 4 kilometers depth, what is living down there, and what could that tell us about, some of these other places like Europa and Enceladus, some of these moons around the large planets.
I was reminded when we talked earlier this year to Helen Scales about the deep ocean. At the same time that we knew that all the moons that you would find in the solar system were cold, icy, dead places, we also knew that the deep ocean was a featureless, empty, barren thing that could not support any life.
Yeah.
Well, that was wrong.
Yeah, and she brings up extremophiles quite often in the book, which biology.
These bacteria living in these sulfur black vent things on the ridges.
Black smokers,
You've got things living down there, like in a complete absence of sunlight. And I think, people are like, oh, okay, well, that's just, things living in the dark. But it's not that simple. Like everything we know on the surface of the planet relies on sunlight. It either requires sunlight to make its food, or it eats that plant or thing that has made that food with the sunlight. So we require sunlight for life. And I think, that when you remind yourself of that, because even if, you studied biology, you sort of forget that sunlight is so important. We go down to the depths of the ocean and there just is no sunlight whatsoever, but there's these organisms surviving. And it turns out they're surviving on the weirdest things, like of chemicals that are coming out of the Earth itself, out of these black smokers, as you mentioned. But also some of them survive off, the radiation coming out, like the infrared light that's coming out from the glow of the volcanoes down there. So it's just incredible, because then we're kind of like, oh, okay, so the life that we think could exist out in the solar system, we need to put our thinking caps on and go, it's not going to look like us, of course. Well, why would we expect that? If it's going to be at the base of an ocean on Europa, then it's much more likely to look at like these weird organisms that are at the base of our own oceans, and that we need to go and study more. And these organisms are like the base of a whole food chain, which we don't understand very well because we haven't studied it. But there's crabs, there's all sorts of things down there surviving, and quite big things as well. And I love I mentioned also there's this Sharkano, as I called it in the book. There's Kawatchi volcano. It's this weird environment under the ocean, but it's quite acidic, it's quite warm at times because there are eruptions happening. So the ocean temperature is warmer than it should be. But there's organisms, big sharks, that will go into that region to get food and to survive. But they won't stay there long, but they can survive in that environment and they can interact with it. And I think they shouldn't do, because it's far too warm for them. So they, naturally shouldn't be there. But this is really cool, that we can study these undersea volcanoes and learn so much about the organisms that survive down there.
Yeah. And, one thing your book did for me was disabuse me of what I've always known about volcanoes is like, oh, it's hot under the earth. And that's why we have volcanoes, because this heat has to come out somehow. And whether it's exploding rock or magma or something, your book showed, oh, all you need is some sort of heat differential. It can be ice. And then, but that ice is a little warmer than the rest of the ice.
Yeah.
And that's where your title comes from, Fire and Ice. So I'd love to have you talk more about the ice of the volcano.
Yeah, because I think so many people don't know there's volcanoes made of ice out in the solar system. And actually, again, it's that Earth-centric view, and maybe that we've looked at the inner solar system a lot. We think volcanoes should be made of hot rock. We think they should explode and create ash. And there are a lot of volcanoes in the inner solar system that do that, and many on Io. But when we go out to the outer solar system, there's actually probably many more solar system bodies, or we'll call them, worlds if we want, that don't do that at all. They're made of ice, but they still are volcanoes. And I think that was a big problem when Voyager went out and saw these worlds for the first time, and saw the fact that their surfaces were new and that we knew they'd been resurfaced in some way. And we had this view of what volcanoes should be because of Earth. And then suddenly, the scientists had to get together and figure out, hold on, what is a volcano? We have this, what's a volcano on Earth? And we kind of have a good idea of what that should look like. But then we go elsewhere, we're like, oh, hold on, these are volcanic features we're seeing, but these volcanoes don't look anything like we expect them to look like on Earth. They're not conical features, they're not even made of rock, they're not hot. So, how do we define what a volcano is? So, as we went in planetary science, as we went out, it really started redefining that volcanology world. We've got volcanology on Earth, and then we need to consider it out in the solar system and far beyond. So yeah, we've got, for example, ice worlds that sometimes have kind of conical features that look like volcanoes, but a lot of the time, like we see on, we can get on Europa and Enceladus, sometimes it's just plumes of material shooting out of the surface from an underwater sort of reservoir of liquid. Now, you could call that an ocean. Sometimes we call these ocean worlds because they've got this crust of ice on the outer surface, and then within them, they've got salty liquid water. So very much like our own oceans, but I prefer to think of it more like their mantles. So we've got on our own planet a crust of rock, and then below that we've got a molten version of that rock, or a warm version, because it's not actually molten at our mantle, but it flows and it moves. It's a different sort of rheology to the surface, and that's the same as we see in these icy worlds. It's just that whatever they're made of, their bedrock is ice, and if it's a little bit warmer as we go down towards the core of that world, it's obviously that ice turns to liquid. So what we're seeing as these plumes shoot out of somewhere like Enceladus, a moon of Saturn, is that you've got an eruption of that material from the inside of that world coming out because it's got a warm rocky core in the middle that's heating up its mantle of ocean and shooting material into space. So we need to rethink, like, is that a volcano? Well, yes, it is a volcano. It's a volcanic feature. It's just not like we see on Earth. And we see, for example, on Pluto, flowing material. We've got glaciers moving. We've got these weird features in the ice where you've got upwelling happening. So you've got basically an exchange of temperatures. You've got, ice that's a bit warmer upwelling and then going back down again and creating these cells on the surface when you look from the top, almost like a big lava lamp, they've likened it to. So we're seeing all these weird features, and it's all volcanic. It's all happening because the insides of those worlds are warmer than the outside. It doesn't mean they're hot. It's not, hot enough to melt rock, but we don't need to melt rock because we've got ice. We've got, different forms of ice, methane, or, nitrogen, or ammonia, or water, whatever it might be. And yeah, so we just need to rethink what's a volcano and what makes a volcanic world.
And I was interested in how do planets heat up? In fact, I'm sure I don't have the whole list, but first is collision, things colliding into the planet, sinking metal in the core, nuclear heat, meaning radioactive elements. I guess you can clarify that one a little more. Radiative heat, that's not exactly one of the things, but like Uranus does not have radiative heat, but Neptune does. That to me was a surprise. And things like tidal heating, so action of gravity on, so if Saturn's acting on some of its moons. So
that last one was the big surprise. So the image that Jeff showed at the beginning of Io, that same year, and actually just a couple months before that image was returned, some scientists had sort of predicted or hypothesized that this could be a possibility. They'd done their calculations and decided that because Jupiter is so large and it has so much gravity associated with it, that these small bodies that orbit around it are affected by that gravity as they go about their orbit. But also Jupiter's Io is one of the Galilean moons, and it's in kind of an orbit with 3 others, and they all interact with each other. So as they go about their orbits, they can sort of pull and tug on each other a bit with their small amounts of gravity, related also to the gravity of Jupiter. So basically, we just take Io on its own. Io is rocky, and as it goes about Jupiter, it's sometimes a little bit closer and sometimes a little bit further away. So Jupiter's gravity is kind of pulling and tugging on the interior of Io. And it doesn't sound like very much, but we call this tidal heating because it's literally doing the same thing as happens with our Earth's oceans. We're changing the shape of that world such that actually we're creating friction within the rock within inside it. And that friction and the heat that's created is enough to melt rock within Io. And it
Amazing.
sounds completely crazy. And this was predicted. And everyone was a bit like, oh, that's ridiculous. Of course it's not. We're not going to find an active world. It's so small. It's going to be long, cold and dead by now. It just can't have any heat associated with it. And then obviously these images were returned of Io erupting, hot lava into the atmosphere, and you're like, oh, okay, hold on, this might be right. And then sure enough, the same thing happens at Europa. This is why Europa has a liquid ocean below its icy crust, because it has a rocky core, which is again pushed and pulled and squeezed, and creates a little bit of friction that creates heat. And we see the same thing at Saturn with some places like Enceladus. So this tidal heating wasn't known about until really the 1980s, really, that it really became well known that as a possibility of a way to heat worlds. And that's when things really started to open up, because before that, we thought the only way to heat worlds was all those other ways that you'd mentioned, that we sort of create worlds from collisions. We create basically, the idea is that we think this is how worlds were created. We end up with these kind of smaller bodies, planetesimals, at the beginning of the solar system formation. And these are just blobs of rock that are very hot. They all start colliding with each other. And the kinetic energy, when they collide to create bigger and bigger worlds, then is turned into heat. And that's kind of what melts these worlds and keeps them molten. And gradually, once things calm down a bit within the first few million years of solar system evolution, these worlds start to cool down and create a crust on the surface, and they're still molten inside, and gradually they cool down. But then because they're rocky worlds, we know they've got radioactive elements within them. So the fact that our world is quite big still, we still have a lot of heat left over from the formation, which is called its primordial heat, what it had from the beginning. But we also create heat continuously. About half our heat given out from Earth is created from radioactive decay of elements within our crust and mantle. So that just keeps our planet warm. So we're kind of like the perfect situation if you want to create an active world. We're not too big, we're not too small. We've got enough heat within us that we can keep processes going. But you go to somewhere like the moon, because it's smaller, it never had as much heat in that primordial heat to start with. And then because it's smaller, it doesn't have as much mass, so it doesn't have that radioactive heat. And it's long since cooled, and that's why it's now pretty much dead, although it is still quite warm inside, but not warm enough to create molten rock. So we expected that every world in the outer solar system that was small, all these moons, should also be cold, just because they will have lost their heat. And that's where this tidal heating comes in. We suddenly discover that actually there's other ways to heat planets, or to heat moons around planets anyway. And that's really a never-ending process. As long as that moon is next to that large world, it's always going to get heated. So yes, these worlds, could be heated for much longer than the Earth potentially.
Can we do a quick order of magnitude check here about a couple of things? Like when we say that the interior of the Earth is hot, I'm shocked at how hot it is. And when we say, well, it's taken longer to cool down, I'm shocked at how long it actually takes for a planet to cool off, and things. I don't know, a couple of numbers, if you please, which I just find startling still. I don't know why. I used to be a thermal physicist. I should know better. But
Oh, you're going to test me on actual numbers, are you? I'm hoping you're going to throw some numbers at me.
Roughly. It's like, so it's like you say the interior. I can be, John Q. public for minutes. Like, so you say the interior of the Earth is hot. You mean like it could boil water, or maybe it's like, whoa, 400 degrees?
No, way hotter. So this interior of Earth is actually hotter than the surface of the sun. And obviously, I mean, I think, because when you talk in real numbers, first of all, I can't remember the real numbers, but I think the reason that it's hard to remember these things is because it's just unimaginable numbers, So the one I always remember is the surface of Venus is, I think, 420 Celsius or something. So it's hot enough to melt lead. It's numbers, and then you go, oh, it's hot enough to melt lead. Like, that's ridiculous. That's very hot. And then I think, we all know the surface of the sun is very hot. We see it blazing away. And so if we know that the interior of our own planet is hotter than that, I find kind of those analogies easier than doing actual numbers. But maybe, I think, again, it's like the distances in space. These doesn't mean anything until you kind of say, oh, it takes 300 times longer to get to this place than this. Like, oh, okay, what does that mean? Oh, that's 6 months, that's 3 days or something. Everything is very hard to imagine.
Well, we could trade it. It's like, no, we still haven't cooled down. It's only been 4.5 billion years. And one that's always shocked me is like, 2 hydrogen atoms fuse in the center of the sun. A photon is produced from that. It takes 20,000 years for that photon to make its way to the surface of the sun.
Oh, wow. Okay, that's a good fact. I like that.
So it's like, and it only takes 10 billion years for the Earth to cool off. Like, really?
I know. Yeah. So half our heat is still from the formation of our planet, which is and also the fact that the center of the moon is still hot. I can't remember the real numbers, but it's the point when a planet sort of dies, when it can't be active any longer, is when the heat is so little that it can't melt rock. So we're talking, you probably need, obviously it depends on pressures within planetary bodies, but if you want to melt some rock, you're going to need temperatures around 1,000 degrees Celsius, but that changes as you go to different pressures. So the temperatures within the moon are much, much higher than that, but because of the pressures involved, we don't melt the rock there any longer. But it doesn't mean that there aren't necessary pockets of sort of more molten material within the moon still. And some people suggest that there could one day be a sort of a very small eruption of material onto the moon's surface. It's very unlikely, but it's not
hold your breath.
It's like it would be a very kind of last spurt of activity, almost like squeezing some toothpaste out of a tube. It wouldn't be a big eruption, but you something could happen because there is still heat within that world, but it's no longer active enough to sustain an atmosphere or liquid water on the surface or anything exciting like that. But it doesn't mean it's completely dead.
And you had a nice discussion about a number of things that behave differently and where a planet ends up depending on how quickly it cools off or doesn't cool off, and that a lot of differences between Mars and Earth, which are otherwise very similar bodies as things go, are very different because they cooled off at different enough rates.
Yeah, and that's what kind of size is everything. Size is everything to a point, and then location becomes really important. So Mars is about half the size of Earth. I think that's always quite surprising for people. Venus and Earth are very similar in size. So, but again, they've also had very different outcomes. But it might be that Venus is not that different to Earth, actually, but we'll learn more about Venus in the coming years. We've got a lot of missions going there soon. I think it's a real planet to watch. But in terms of Mars, because it's half the size, it cooled so much quicker than our own planet. So it just couldn't sustain all the things that we could sustain, and it affects so many more things than we even think about. So we have plate tectonics. That's a super important thing. We think plate tectonics is probably quite important for having life on a planet. It definitely shows the world is active and it's able to renew its surface. It allows the planet to release gases into the atmosphere. There's a lot of things that help a planet if it has plate tectonics. But we are the only planet we know of to have plate tectonics. So again, it's this, we have one data point. Mars probably has never had plate tectonics. We're not 100% sure, but from what we can see at the moment, it never developed at wide-scale plate tectonics on Mars, and that's because it just cooled too quickly. Its crust just probably became too rigid too quickly, that it just couldn't subduct. It didn't have enough water on the surface for long enough to kind of lubricate that process, because water is really important on our own planet for helping plate tectonics keep going. And when we go the other way to Venus, it didn't cool quickly enough. So what happened with Venus is that its surface probably remained too ductile. It's almost like plasticine. It's too squishy to actually be brittle enough to create plate tectonics. So it's these small differences, even though Venus is really, really similar in size and it's made of all the same ingredients as our own planet, it had a very different outcome. And that potentially has affected the fact that it may never have had life. We don't know for sure. It may have had life in the past, but it's definitely had a very different geological history. And if that life existed, there is no obvious evidence of it right now. So yeah, I think, size is really important because all these planets, Mercury, Venus, Earth, and Mars, started out exactly the same. And Mercury, as an example, had a completely different history because it was bombarded by a massive impact early in its history that ripped off its outer mantle and crust. So what we see with Mercury, and the reason it's so small, is because it's mostly just a core. It's like a big, a solid core of a planet, and the rest of it's missing. It's, lost most of its outer shell, which is really sad. And you think, goodness, what's Mercury doing? And it's still an interesting world. It's still contracting, it's still shrinking, and there's stuff going on its surface because of that. But it's almost certainly never had life because of what happened in its past.
Oh,
I know.
Yeah, we're all sad for Mercury now. So yeah, that I felt like the information you provided on Venus for me was very interesting. Just to think that the surface is actually very melty and squishy, and
but it's completely covered in volcanoes. And what we see with Venus is that the really, really cool thing, I think, is that its entire surface is almost all the same age, which may not seem particularly exciting. But as a geologist, when we look at our own planet, we've got a portion of planet from every part of our history. We go back almost all the way to our planet's formation. We've got very, very old rocks, nearly 4.5 billion years old, and we've got extremely young rocks. Literally stuff coming out of volcanoes today is the youngest rocks we have, and everything in between is almost represented somewhere. But when we go to somewhere like Venus, pretty much all of the surface is around 500 million years old, plus or minus maybe 200 or 300 million years, which means that the whole of Venus was resurfaced within that time period. And that in itself is fascinating. So what happened 500 million years ago to create a huge amount of volcanoes erupting all at the same time across Venus's surface? Now, you've got to remember I'm a geologist, so I think in millions and hundreds of millions of years, which is an incredible amount of time. So, it did take a while to resurface that, but we're comparing that to a 4.5 billion year history. So something happens on Venus, and we think it happens on a kind of cyclic thing, that about every 500 million years, Venus resurfaces itself. And the idea is that because it doesn't have plate tectonics, it basically insulates itself with this crust that it forms. So the inside of the planet just continues heating up, and that heat kind of comes out in volcanoes a little bit, but it keeps building up because it just doesn't release enough of that heat because it doesn't have plate tectonics. And then all of a sudden it creates so much heat that it overturns its crust. So basically the whole of that outside of Venus just starts erupting to just release that big burst of heat that's built up over time. Now that's one idea of what we think is happening at Venus. Of course, we need to go there and investigate that surface in more detail, which is happening. I think there are now 5 missions planned for Venus over the next decade, which is amazing. And I think, Venus is going to be the new Mars. It's we're going to learn so much about it, and also about all its volcanoes, because it's got more volcanoes than anywhere else in the solar system. Many of them are like volcanoes we have on our own planet. And so hopefully we can start to learn about Venus's atmosphere. Why is it so, carbon dioxide rich? Why has it got that kind of runaway greenhouse effect, which could be very important for understanding our own planet and our atmosphere? There's a lot to learn at Venus. I'm really excited that we can go there, particularly because it's so volcanic. I think it will be amazing.
So would they have super volcanoes as we have, which everyone loves to talk about? You can't leave
there's gonna be a
talking
lot.
about volcanoes without saying super volcano.
Of course, supervolcanoes. Yeah, I mean, we think Venus has probably about 8 really, really large volcanoes on its surface that are created by what we call mantle plumes. Now, these are hot chimneys of rock rising through the mantle from the core of the planet. We have those on our own planet. Hawaii is the best example, or maybe one of my favorite examples, because that is created by a mantle plume. Iceland is also created by a mantle plume. We've got lots of them, the Galapagos Islands, lots of different places, ocean islands that we see are created by these mantle plumes. So the exact same feature has created some of the volcanoes on Venus, and they create quite big volcanoes quite often, where you get a lot of lava outpouring over time. And when we look back through Earth's history, we see the evidence of really large eruptions happening throughout Earth's history. And these are called supervolcanic eruptions. So supervolcanic eruptions don't just have to be the really explosive things that, where we talk about Yellowstone, one day really exploding big style. Actually, it can be just massive outpourings of lava that isn't necessarily explosive, just there's a lot of lava in a short time scale. But again, we're talking over millions of years. So it's getting your head into that geology world and thinking, okay, it's not happening like in one day we're going to have swimming pools of lava flooding out. It's over a long period of time. But the fact you've got that lava coming out, it's not just molten rock, it's gases coming out as well. And the huge release of gases from the inside of a planet changes the atmosphere of that world and can create mass extinction. So we think in our past, some of our mass extinctions that happened were possibly created by these supervolcanic eruptions over millions of years, releasing gases into the atmosphere. So that's why there's so much to learn from Venus.
Yes. Speaking of gases, I wanted to find a reason to have you tell us a little bit about your contribution measuring the ratios of helium isotopes in rocks, which sounds like the most esoteric and useless thing, except that I used to work a lot with helium, but it is not. And this is my way to circle back to a specific example of something that fits into a long chain of inferences. So would you tell us about what you did and why it was important and what you were able to deduce from what you found?
Yeah, so I loved that I got to write about this in the book. I think I wasn't going to write a book on volcanoes without talking about what I worked on for my PhD thesis. Because you don't get to do that very often. So the rocks I worked on came from what we call the Proto-Iceland plume. So I mentioned that there's a mantle plume at Iceland today. And Iceland so happens to also be on a mid-ocean ridge. So it's kind of like, it's these two things working together to create this massive volcano, volcanic island, Iceland. Now, we can trace back that volcanic edifice 60 million years. And at the time, if we kind of have to go back in time and restitch the world back together, because over time, the mid-ocean ridge has started spreading and, Iceland has grown up in between. But before that, 60 million years ago, the eastern seaboard of Canada, Baffin Island and regions in Greenland were connected to Scotland. And then over time, as this mantle plume erupted, these two continents split apart. So what we see in places like the Moluccan Tyre and Skye, and on the eastern side of Canada in Baffin Bay, are the exact same rocks. These were erupted at the same time, and they can be traced, we can date them and trace them through history. Now, these rocks are really important because they represent one of the most primitive mantle plumes. Now, this is where things get quite interesting. So we think that this plume that came up from the core of our planet is sampling the oldest material that we've ever sampled in our own planet. And when I say old, we think this material literally was contained inside the planet from the formation of our planet from 4.5 billion years ago. So that material that's contained in the core that came up in this mantle plume, this hot chimney of rock, and impacted the surface and created volcanoes 60 million years ago in Baffin Bay, that contains gases that were formed from, the solar nebula that created our solar system. It's sampling the very earliest materials that formed everything that we see today around us. So if we can sample those rocks and find traces of those gases trapped within those rocks as they erupted and then encapsulated the gases in crystals that were growing, we can sample those gases and find out what our planet kind of looked like when it was formed. Therefore, what the atmosphere was looking like. So the gas that I worked on, as you mentioned, was helium. A lot of people know helium because of helium balloons. Oh, brilliant. Well, that's there we go.
Oops, sorry.
Hawaii.
Somewhere
And that's
go.
not been working in Iceland. That's over in Montserrat, but I can come on to that after. But yeah, I have done quite a bit of field work over the years.
Very
Sadly,
cool.
I never went to Baffin Island. So yeah, that was the Caribbean, a somewhat warmer environment to do field work in.
The plume of gases, as you say.
Oh, brilliant.
Yeah.
So yeah, I measured the helium gas that was trapped within crystals of olivine, which is like the peridot. You might know it as a gem. So olivine traps this gas. You can crack it open in a laboratory in a special instrument, and then you can analyze those gases. And what we're finding out is how primitive that gas is, how old is the gas contained in that rock. And what we found was that it was extremely old. And actually, the gases within those early Iceland plume rocks were the oldest that we've seen ever within our planet. And this tells us that reservoir that it's sampling has literally not been touched ever since. So it's just, it formed 4.5 billion years ago, and then it wasn't touched. And then I was the first person to kind of ever see those samples that were created all that time ago. And you can obviously combine that with many other analyses within those same rock samples to understand more about how that rock formed and where it came from. But the helium gas, that was a really exciting thing to work on.
So very, very glad you shared that in the book, so because it gives us insight, your fascination with volcanoes everywhere and your vast knowledge, that you really understand it deeply. I thought I'll share this. Jeff might find this interesting. He keeps threatening to have all my children come on Read Science, because of course I got 4 kids, 3 are scientists.
That's brilliant.
And so you have a sentence here: although volcanism is often studied in isolation, it is joined by atmospheric science. My son's an atmospheric scientist. Geology, my other son is studying geosciences. Hydrology, my daughter is a hydrologist. And possibly even biology. And I was like, how can that my whole family be there? Except we need to add a Spanish speaker, but then we're good.
But I think that's what I didn't realize about geology or earth sciences, whatever you want to call it. I think, it's kind of getting a bit of a rebrand recently, because geology gets a bit of a bad rep, because people think, oh, you just look at rocks. What's so interesting about that? And I think actually talking about geosciences or earth sciences makes it sound a bit more modern, but whatever you want to call it. What I didn't realize when I first started studying it was that actually you kind of need all these different scientists to help you along the way, and having a good background in maths and physics and chemistry is actually really important. But then working with, I love working with biologists. In my current job, we have an astrobiology department. So these are mostly microbiologists that are now working on understanding how organisms survive in space, and what kind of environments we need to look at. That talking about extremophiles and things. So I guess as a biologist, you'd never think initially, 20 years ago you'd probably think, I wouldn't work in space. That doesn't make any sense. Maybe you might work as a medical doctor helping astronauts or something, but not actually doing the pure science research. So it's just fascinating, all the things that play into planetary science and geology. It's great.
I'm not going to read the paragraph in which you explain why you think you prefer geology much more over physics.
I do remember that.
Yes, but it takes all of us, doesn't it? And working together. And so I've shared this picture that we can talk over as we sort of start to wrap up. This is another picture of Io. This one was taken in 1997, flips around, by the Galileo orbiter mission to Jupiter. And sure enough, there's still one of these volcanic plumes or whatever. But the amount of progress we've made, even in doing the photography in the 20 years between those two pictures, is, I still think, is very startling and amazing.
Yeah, and I think, every mission that goes back, again, it's like you're taking a picture, but then you're deciding what kind of resolution you want to take these pictures at. This looks like incredible detail compared to what you have from 1979. And the images that are going to be coming back from the Jupiter system within the next 10 years are just going to blow your mind. We're going to be looking at tiny regions in so much detail, and that's where we really start to pick apart. It's going to keep scientists going for decades, trying to understand the information in these images, which is kind of touching on what we spoke about at the beginning. And one of the great things we can do, particularly with somewhere really active like Io, is compare what we've seen, 20 or 30 years ago, or even further, with what we see today. Has it changed? What's changed on the surface? Even if we've got relatively low resolution images, we've seen that happen over the time. We can see there's a crater lake on Io that we've seen change. So we know that it's erupting. We can see how it's acting over the years and when it produces plumes, and that it has a periodicity to its eruptions, that we've been able to find that out just by doing flybys and not even concentrating on that one region in particular. But yeah, there's the fact that there's lava lakes on Io is, I think, absolutely amazing.
If I read about this correctly, not only do we have this plume that we can see in a similar way that we could see the one earlier, but I believe this is also a volcano here, and you can see there's a plume of gas coming out with a shadow.
Yeah.
And it looks like a cone that goes with it, and all those features that you want of a volcano, at least.
Yeah, so Io is probably the only moon out there to behave like we expect it to behave. It behaves like in the inner solar system. So I love it because, I mean, it's very much like an early Earth. We could say this is somewhat like Earth looks like probably 4 billion years ago or so, just when we had an early crust, and the rock type is very similar to the early Earth. It's different because the planet was hotter and Io is hotter, so it creates a slightly different type of basalt at the surface, but it's still essentially a type of basalt like we see on Earth. So we can study Io to sort of understand what happened on our early planet, the bit of our history that we don't have a lot of rocks preserved from. So it's nice that we can kind of look at planets and learn about the bits that are maybe missing from our own history.
It's really amazing, really amazing. Well, we are here at an hour. It's been wonderful to have you back on, Natalie. I'm going to ask that question again. Are you going to write another book? Or have you reached that limit?
I am planning at the moment a sort of kids version of maybe a mixture of the two books at the minute. Okay. So I'm working on a proposal, which I've been working on for a while, but I hope to create some kind of a very illustrative book, but with a lot of information for sort of 7+, hopefully. Okay. So it's a real challenge, actually. But I think I would really enjoy to do that. I think partly because I've got a young child now, and I've seen kind of understood that world of what children want to know about, and that they can read at quite a young age, and actually there's a lot of information they can get for themselves then, and having a lot of pictures and books, and they can learn a lot from that. So that's what I'm hoping to do next, but we'll see. It's tricky. These books take a long time.
They do. Well, yeah, we've definitely had a lot of guests on who've written children's books and middle school books, and so they're an important audience for science as well. And you never know what thing will inspire someone to go into science. It could very well be your book.
Yeah. So. Exactly. No, and that's something that's really important to me. Just I want kids to enjoy science, particularly girls, because I think geology and physics doesn't appeal to girls, and I think that there's a whole discussion to be had around that. But I think if as a woman scientist, I hope that I can inspire children and show them that actually there is a whole career to be had, even though I'm no longer doing science itself.
You're still a scientist.
Want to be communicating it. Yeah,
can't take it away.
Exactly, that there's a passion for it, and that you can do that and still have other interests in life, and enjoy science and be inquisitive, and that I think that's really important.
We're so glad you joined us, and those of you watching, we've been talking about Natalie Starkey's book, Fire and Ice, the Volcanoes of the Solar System. And if you like that, or you want something a little different, she wrote another book called Catching Stardust, Comets, Asteroids, and the Birth of the Solar System. Both of them are great, very readable, lots of good information. So,
thank you.
Thank you, everybody, for joining us. Thank you, Jeff, as always.
Thank you, Joanne, and thank you, Natalie.
Thanks for having me. It's been really fun.